So today we're going to start to talk about numeric values and actually quantifying equilibrium. And so what we're going to deal with is called the law of mass action, or an equilibrium expression. So for any reaction where you have A and B yielding C and D at equilibrium at a given temperature, the equilibrium constant, Kc, is equal to the product of the products, the concentrations of the products, each raised to their coefficients from the balanced chemical equation, divided by the concentrations of the reactants, which are each raised to their powers from the balanced chemical equation. So yes, this looks a little bit like a K expression from kinetics, but it's very different. Okay, so you're going to have to keep equilibrium and kinetics separate in your mind. Well, Kc is a measure of the extent to which a reaction occurs. It varies with temperature and only with temperature. Also, it's unitless. Okay, so let's start by just writing a couple of Kc expressions. Let's say we have this guy, PCl5, in equilibrium with PCl3 and chlorine gas. It's going to be products over reactants. And you see this is balanced. All our coefficients are 1. So we're going to have the concentrations of our products divided by the concentrations of our reactants, and they're all raised to a power of 1. Okay, these brackets are what we use for concentration, for molarity. Remember that we can only have the concentration or the molarity of something that is aqueous or gaseous. We can't find the molarity of something that's like a pure liquid or a solid, but you won't see those. Okay. So let's try this one. We have 4 ammonias and 5 oxygens yielding 4 nitrogen monoxides and 6 waters. So it's going to be products over reactants, and we're going to raise each one to its respective coefficient as an exponent. So NO to the 4th times the concentration of water to the 6th divided by ammonia to the 4th, oxygen to the 5th. Okay, so we can write these expressions. Now let's actually try and use one. It says 1 liter of the equilibrium mixture from example A was found to contain 0.172 moles of phosphorus trichloride, 0.086 moles of chlorine, and 0.028 moles of phosphorus pentachloride. Calculate K. So we write our Kc expression, and then we're going to plug in our concentrations. Well, notice they gave us moles. However, these are all the moles that are in 1 liter, so if we divide everything by 1, the concentrations work out. Yay, that's so nice of them. All right, so we're going to put our values in, and we get this, 0.53. Now, if you are dealing with something a little bit more complex than this, I want to go ahead and caution you to use your calculator carefully. Parentheses, things like that are your friend. Okay, so what does this 0.53 mean? Like, what's the deal with that? Well, if Kc is much greater than 1, then most reactants will be converted to products. In other words, this would be a product-favored reaction. Well, think about the form of Kc. It's products divided by reactant. So if we have a lot of product and not a lot of reactant, we have a lot of numerator and not a lot of denominator, then K will be much larger than 1. And if it's much less than 1, then the converse is true, that we have mostly reactants, not products. Again, think about it in terms of the fraction. We have a lot of denominator, not a lot of numerator. We get a value that's much smaller than 1. Okay, so let's try something that's a little bit more complex. 0.2 moles of nitrogen and 0.2 moles of hydrogen were allowed to reach equilibrium in a 1 cubic decimeter closed container. At equilibrium, the concentration of ammonia was 0.06 moles per cubic decimeter. Determine the equilibrium concentrations of nitrogen and hydrogen and calculate the value of Kc. So first thing, we need to write ourselves a balanced equation. We've seen this before. And what we know is that initially we had, okay, that alignment's off, 0.2 moles of nitrogen, 0.2 moles of hydrogen, but only 0 moles of ammonia. Okay, and these were all in 1 liter, so moles divided by 1, and yay for concentrations. And they tell us that at equilibrium, well, here's our concentration of ammonia, it's 0.06, but we don't know the nitrogen or the hydrogen. So how are we going to do this? Well, ultimately, guys, we're just going to use some stoichiometry because this is both moles and its molarity since it's or the numeric value is the same since it's in a 1 liter container. Then we say, okay, we'll add 0.6 moles of ammonia. And for every 2 moles of ammonia that we get out, we put in 1 mole of nitrogen. So we're going to use a mole ratio. Well, that means that 0.03 moles of nitrogen must have reacted, which means 0.2 minus 0.03, 0.7 is our equilibrium concentration for nitrogen. And we're going to do the same process for hydrogen. Our moles ratio is going to change a little bit. It'll be 3 over 2. We get 0.09, and we'd subtract that from our initial 0.2, so 0.11 is our concentration of hydrogen. Okay, so we just did that first part. Now we're going to calculate the value of Kc. So we have our equilibrium concentrations now. We're going to write our Kc expression. It'll be products over reactants. So ammonia squared over the product of nitrogen times hydrogen cubed. And we're going to put in our values. So grab yourself a calculator. Actually try this. See if you can do it. We get 15.9. And if we think about, well, what does that 15.9 mean? It means that we had a lot more of our product than we did of our reactant.